The next team on this session is their customer is Jonathan Tang, a former ECE graduate who's at Raytheon, and their project is a grocery shopping robot. Many of you may have walked in and saw these funny little tables outside, and you also see a robot moving later today. So this is team number 9, grocery shopping robot.
Good morning, everyone. We're Team Kinetic. We built the Shuffle, the automated grocery shopping robot. My name is Gurwinder Singh. I head the pathfinding and QR code detection.
Ngozi, I worked on the customer website.
And you are one of the asset protection. I'm Dr. Chang. I work on the hardware. I'm John Furst. I did the navigation.
So our main objective for this project was to build a cheap, automated way to detect items in a grocery store. And a second requirement that we had made by a customer was to develop a robust pathfinding algorithm that would optimize speed and power. So we had 3 main things that we made for our project. We made a website, model store, and the main piece, the shopping robot itself. So for the website, it just had to be a basic website. You could pick a series of groceries you would like to pick up, and the robot would go out and retrieve them for you. The model store was mainly made for our own testing to see how our robot functions. We have it outside. And the main piece is the shopping robot, which basically navigates throughout the store, scans barcodes, and finds things corresponding to the list that was made on the website. So this is a broad overview of what we made. There's a sonar sensor which goes into an MSP 430, which is embedded onto our PCB, which then goes to our central hub, which is the netbook, which then feeds it directly to the iRobot via USB. There's a bunch of other, we have a webcam which feeds the QR code images to the netbook, and the website as well feeds the grocery list itself to the netbook. So from last semester, we had a quick prototype we made, and we potentially decided to build our own. So we driven down the cost to about $600. So we have some custom parts that we used. So this is a basic overview of what our store looks like right outside. Another view of how the shelves look like, and this is how the item layout looks like. And then the guys can talk about the website.
So the basic goals for the website is to make it intuitive and easy to use for the average customer. And then, of course, it would take customer orders and transfer that information to the shop bot so that those items can be picked up. This is what the website looks like. This is just one of the pages of the website where a customer would be shopping for actual items, and you can also see that you can give information about who you are, so you identify yourself when you're picking up an order, and there's payment information and pickup information, so you can specify a time to pick up, and you can pay online. This is what the server looks like. This particular page shows the table for items. So, for instance, based on an item, you can find out how many of an item there is, the price of an item, and so on. This is what the website looks like that we use to push our website live. So this is how we control the website from here. This is what we use to connect the website to the shop front. So what you think here is a list of item IDs on the right, and the quantity of the items on the left. So it's a quick numerical summary of an order. This is an example of code. This is how we connected from the website to the database.
For after detection, basically we want
obstacle detection, you basically want to transfer the distance from the obstacle closest to the notebook, so the notebook is set up a threshold for stopping and alerting someone to remove the obstacle. This is what the overview looks like. The sonar sensor will communicate with the MSC40 by converting a analog voltage, which will then be sent to the notebook via the UART. This is basically the code outline. The first part of the code will set up the ADC and UART. The second part will obtain 3 samples and average them. And then I'll apply the conversion formula, and then the number will be converted in ASCII format, and then I'll send a new line, and then the number will be wiped to the buffer, and then the number will be sent to the notebook via the UART. This is the conversion formula. The ADC 10 mem is the value obtained from the ADC on the MSC 430. Vref is the reference voltage that you said earlier in the code. V2 to inch is determined by the solar sensor, which is proportional. The ratio is proportional to the input voltage, and it depends on the scales relative to how far the closest obstacle is to the sensor. And length is the output, which will be sent to the network.
Hi. So I was in charge of the hardware part of our project. So my job was to make and design the printed circuit board, essentially the bridge that connects the sonar sensor to our network. So one of the main problems that was encountered in designing the PCB board was understanding the communication of our PCB. The microprocessor that we use, the MSP430, only communicates using UART, while the network uses USB communication. Therefore, a converter is needed. So the sonar sensor sends data that it receives to the MSP430 through an analog line. The MSP430 then sends it to the converter through UART, and the converter to the mini USB through USB, and then onto the network. So this is just a brief picture of our schematic. And this is our printed circuit board. The red represents the top layer, and the blue is the bottom layer. This is a 2-layered board, and the bottom picture is our PCB.
Pathfinding. For pathfinding algorithm, we basically wanted to find the shortest, fastest path throughout the grocery store, given a set of items. And so basically, the pathfinding algorithm itself is a very particular case of the traveling salesman problem. But based off some of our assumptions, we were able to boil it down to the shortest path problem. So some of the assumptions we made was it's a direct graph. You can go more than one node twice. We have a small set of nodes, meaning items. No non-negative weights are equal distance. So basically, an overview of the algorithm itself is we can compute the shortest path between a set of vertices or items and try and find the best combination of that that'll make the shortest path. So this is a quick overview of what the algorithm itself looks like. And so the entire algorithm itself is written in C++, and its running time based off our model store, which is a set of 20 items. It can run in under a second, which is more than fast enough for our needs, since our requirement for navigating throughout the entire store is about 30 minutes. So it's pretty robust. And so for image processing, we basically have a set of QR codes that are on the shelves themselves, which act as the shopbot's eyes basically throughout the store. So every time it sees a QR code, it will scan the QR code, detect it, code it, and send it to the navigation, telling the robot where it is, what it's supposed to do with that. And so basically, we have to make sure that the QR detection is very, very fast, in milliseconds. So we used a couple of libraries that were already pre-made that provided us to quickly develop and make sure that our detector and decoder was very fast. So we used the Xilinx library for decoding 2D barcodes and QR codes. It's basically all written in Java. It's very robust. It's been out for a handful of years. It's on the Apache license. And so we also used a webcam capturing library, which basically is also under the Apache license, which allows us to directly inject real-time web feeds from a USB webcam or the webcam embedded onto the netbook itself and send it directly to the rest of your Java code. So a broad overview of how the QR code is running. We have a Logitech HD webcam, which we're using. So it reads a device that we need to read, which is the USB device, which is listed under Dev Console. And then we set it up, after getting the feed, we set it up for real-time streaming, feed it directly to our Java code. It then pipes to our QR code encoder, and then it outputs to a pipe that we have set up so we can communicate with navigation. So, can you talk about navigation?
Yeah, so navigation is sort of a robust part of the robot. It controls all of the robot movement, as well as I think you saw in the previous slides, that everything ends up sort of going back to the netbook here, and so it was controlling all those different things. Before I go on to it, I want to show you this picture of the iRobot Create, which is what we use as our robot base. If you can see the purple things at the top and on the sides, those are what are called lift sensors. And so these are the things that if you were to have an iRobot, like a Roomba, they prevent your robot usually from going down your stairs, or if you had it on something like that, basically they detect like the distance to the floor. They're infrared emitters, and then they detect how much is reflected back. You can actually use these to detect colors if you want. And so we use them to sort of do our line following. And so you can see the two at the middle front. And so basically the line is in between those two, and if one of them hits, the robot spins the other direction. So that's just an idea of what the sensors I'm talking about. I may refer to them as cliff sensors, because that's what they typically are. So the navigation is a lot of things that it's responsible for. So the first thing it has to do is it has to calibrate to the environment. So every store might be different. It has different color tile or carpet in our case for today, different color lines, whether they be black or white or something hopefully that's very different than the floor. And so basically the first thing that you have to do when you set up the robot is have the navigation learn what it's supposed to be looking for. And so it needs to calibrate to the floor and calibrate to the lines. That's all automated, but you just need to go through its process. It will prompt you for all that. The next thing that needs to happen is that the robot, it has no idea what the store looks like, so it needs to learn what the store is. That's part of this project. And so the first time through, the robot navigates through the store, having really no idea what it's looking at, and along the way it's scanning QR codes, and when it comes across a QR code, it has to save that position in its sort of own map to then be generated with all the path planning stuff. And then it's ultimately, the navigation is responsible for when an item is requested of the system to be able to transport the robot from wherever it is to that requested item via the shortest path possible. And then obviously overall just moving the robot around in all cases. So as I said, the navigation sort of is this central hub of all these different sub-modules that we were talking about. So it's actually a multi-thread application, fairly complex. It's constantly communicating with the QR program, which is a separate program via inter-process communication. It's constantly communicating with the path planning program, which is telling it where it should go. It's constantly communicating with the sonar module, making sure it's not going to run into anything. So you have all these different threads going on at the same time, and it's trying to mix and mingle all these different things to do the right thing. Just to give you an idea of how it works, it's a line-following robot. As I said earlier, it has those two infrared sensors at the top. We calibrate all those sensors to the floor, and just sort of basic idea, if we hit the line on our right sensor, then we need to rotate our robot to the right to prevent us from going across the line, and then vice versa for the other side of it. Along the way, we basically keep a history of our saved movement vectors. We do this so that, I'll talk about it in a second, basically if we get off the line, we can kind of get back onto the line. One of the things that we have in our store is we have multiple shelves in our store, which provide us with joints across lines, so intersections of these lines. And so we need to be able to detect those joints and to, we'll call those joints or intersections, and at those intersections, we need to be able to, when needed, traverse them correctly. And so basically the joint detection algorithm works in the sense of you have the robot driving straight down a line, and think about you coming to like a T joint. When you come to a T joint, there will be at some point when both of your line detector sensors will trigger at the same time because they both see a line in front of you. That means that we know there's a joint there. Once we do that, we have some logic of how to handle the joint depending on which direction the joint we want to go. We want to go right, left, or straight, which angle we came at the joint from. So line finding, this is basically a preventative or a safety measure in the sense of every so now and then we want to make sure that our robot hasn't like gotten off the line, it's just going in the middle of nowhere. So basically what happens is if the robot has detected that it has not bumped into the line, which usually happens very periodically, or it's constantly hitting either side of the line. If it detects that hasn't happened for a while, it gets concerned and is worried that maybe it's lost its track somehow. So basically it will start to rotate to look for that line, because it should bump into it almost instantaneously. If it doesn't, it realizes it has fully lost the line, and then what it needs to do is it utilizes that history that I talked about earlier of what its movement vectors have been, and does the inverse of that, to go back to the last point it can find the line, and then from there continue on. This actually doesn't ever happen. Our system's actually very robust, and I haven't seen it get off the line for a long time. But just in case, this is in there. And then finally, one of the most important parts is the item retrieval. And so basically, it has to route the path from wherever the robot is currently to the next item that it's being asked to retrieve. Obviously, it has to perform the actions to get there after it's routed the path. Once it arrives at the location, what it has to do is it needs to resolve its orientation. This means that there's a webcam. It's on the left side of the robot as it's driving straight. Sometimes the robot will choose a path to get to an item where that webcam is now not facing the correct QR code. So what it does is it actually stores the orientation of all the items, or aka the orientation of the robot when it found the item. And so once it gets to the destination item, it will fix its orientation to be in the correct orientation. So it might spin 180 degrees if it needs to, so that it can see the QR code. Once it's in the correct orientation, it will scan for the QR code to do a visual confirmation that it is indeed in the correct location, and it can find that QR code. And then basically it plays some tones based on if it did find that QR code, it will beat the correct number, it beat the number of items. There were times that items were requested. If it did not find the item, it emits a terrible screeching sound, which hopefully you won't hear today, but you might. It basically is an error. So I'll let, let's see, central. Well, I guess I'll talk about this for a second. Basically, the netbook, like I said, houses the integration for all these different parts. Basically, having to have all these connections to the MSP430, to the QR, or to the webcam, and to the iRobot itself, as well as the sonar sensor.
Sure. This is the website to the netbook is kind of what you saw earlier, but there's a list of items in the database. When the netbook visits a specific website, it can view all of the items that have not been processed yet. And as soon as it goes to that website, the database is updated and a new list starts being made. So that's how that works.
So I spoke about this before, where basically after receiving, decoding, getting a result from the QR code decoding algorithm, it sends it over to navigation via a 5-foot pipe we've set up called QR comms, and then the navigation system itself handles the result taken from the QR code.
The sensor would periodically pull the ADC on the MSC40 launchpad, and then it will be the voltage will be converted into ASCII format of them, and then the number will be after the UI conversion.
And then finally, I talked about this, but so the iRobot Crate actually has a serial port on it, a proprietary serial, proprietary iRobot 2 serial port, and then since not many things use serial anymore, we use a server to USB converter. And then just to give you an idea of the type of commands that we're sending to it, I mean, these are all encoded in opcodes and with different parameters, but to give you an idea of what they are doing, we're sending a lot of commands to the iRobot to tell it to drive either at some speed or at some angle, and that means like a radiated a spin on it, basically, to literally turn around either sometimes 90 degrees or 180 degrees. It has no notion of that. We have to figure out what 90 degrees and 180 degrees means, and we use that sort of based on our store, and we do a lot of sensor feedback of when we are spinning and we're looking for lines, and once we pass the number of lines that we require, like maybe in our case it's 2 lines across an intersection, we know it's spin 90 degrees. And they're all obviously always pulling these sensors all the time. There are optical encoders in the wheels that give us a notion of the distance we've traveled, and there are the click sensors which we're using all every time to start line navigation. And finally, the last thing that we send to the robot is asking it to play a song for us. This is based on item retrieval or item failure. Also, play some of the notes when the store has been finished initializing, and just to give the user some feedback. Anyway, so thank you very much, and if you have any questions, I'd love to have. Oh, and thanks to all the professors.
I was at the supermarket yesterday just thinking about this problem, trying to find your item, and when you go to the customer service counter, they call the department, and the department says go down aisle 3, and you still can't. However, your talk is all about robots, microprocessors, websites, databases. I have no idea what you're doing to solve this problem. Could you just back up about 5 steps and just give us an overview of what you're doing, interfaces to what a shopper in a grocery store would be doing? Am I supposed to take my iRobot with me to the supermarket, run the iRobot at night, and store it in its database? Exactly how is this thing supposed to work?
I'll give you a model case. A store, maybe like Shaw or something like that, would buy the system from us, and then they would we'd have to have some very minor installation team with them just to make sure that there are the lines set up within the store and that they have the proper QR codes and everything like that. But the basic idea for a user is that they can log on to the store's website, which would look very similar to the one that Ngozi demoed earlier and we'll show today. And then from that website, they can order the items. It's basically like Amazon or something like that. I mean, maybe not as nice, but they can order their items into a shopping cart and go through the whole payment process. And then the order is submitted to the ShopBot system, and from there, the system handles it completely. The system basically will prioritize orders based on when they are asked to be received by the customers, and then the system will start to deploy its ShopBot to go and retrieve the items for the user. Basically what the use case for this is you can now imagine your grocery store is not so much of a grocery store where humans are going through it, it's an inventory warehouse.
This system is a robotic replacement for the little workers who go and fulfill Peapod orders to be delivered to your house?
Yes, it'd be similar to that.
So it's not for when a customer goes into the grocery store. It's for the grocery store to assemble
It assembles the orders, and then right now, I mean, it's still meant for the robot. Sort of goes back to a home base at the end to deliver its order, and so this would be like the user would come still to the grocery store to pick it up, but maybe the grocery store would have some delivery option also, like Peapod.
One last question. Do you have future plans for an expert system that helps the robot pick best fruit?
Oh, that's actually part of it. So that's one of the things that Gurwinder spoke about with the entire path planning thing is it's trying to solve a subset, the traveling salesman problem, but not with the entire grocery store. Obviously, it's a subset of the items that are requested for that order. Yeah.
Thank you.
Yeah. Hi.
You mentioned you have a netbook on the robot itself. It serves as the hub for all of the software you have going on. It seems like it might almost be more than what you need. Have you ever thought of like a cheaper alternative, maybe something smaller than like a full-fledged netbook?
Yeah, we definitely did at the beginning. So the most computationally intensive tasks of this project are 1, the path planning, and 2, arguably actually the QR decoding. The image processing actually is not trivial. It's actually possible to offload both of those things to a separate server, which was our original plan. We decided not to end up doing that just because it added more complexity, more communications, and more systems. But in a scaling environment, I would highly recommend, and we would probably do this, is we'd have some industrial server doing both the image processing and the path planning, and then all that would just be streamed to the robot. And then at that point, you could reduce the computation on the iRobot itself to be something much smaller, and we could do some sort of maybe microprocessor or something like that, or microcontroller. There's still a lot of USB devices to interface with, but you could probably do that with a Raspberry Pi.
I have 2 questions for you. Regarding your pathfinding algorithm.
Yeah.
So, I mean, how does that scale? You're trying all permutations. You said. I mean, is there a point where I want to order 100 items and that will just take you all day? Yeah,
it doesn't scale well right now. The pathfinding actually was very difficult for us, and so we found something that worked well for small orders.
Sure.
Obviously.
Do you know what range of orders are feasible?
We can do things within 20 orders, but more than that, it starts getting very intense for us.
Yeah.
It would help if we had better hardware, obviously, if we weren't doing this on the network. And then the other scalability also would actually be some type of caching mechanism. It's not infeasible, obviously, especially in a traveling salesman problem like this, to when you know different. This is how real traveling salesman problems work. Is they sort of store a memory of from this point to this point, I know this distance and I can use that. Well, you can actually go sort of meta here and say from this order to this order, it utilizes the same paths, and so it's just instantly do that. So it helps with your running time, but the running time is a different problem when you have multiple orders to consider.
I have a question. So is the robot itself doing the item retrieval portion? Is that like out of the scope of what you guys?
So originally we wanted it to actually physically grab the items. It ended up not being within the scope for us.
It seems like it would be its own senior design.
Yeah, it actually almost was. It was almost a mechanical engineering one, but they sort of started an entire semester after us, and we were just out of sync with them.
And what was the decision behind using QR codes? It seems like a grocery store.
Yeah, they typically use barcodes.
Yeah, you could try and attempt to scan the barcode.
So yeah, we actually chose the QR codes because barcodes, while maybe ubiquitous in stores already, actually have a hard time with if you have just a regular one-dimensional barcode scanner and only one axis of scanning, it's actually you have to line it up pretty accurately, 90 degrees perpendicular to it, or to its normal, to correctly scan the code. QR codes are much more lenient. You can scan them from actually very ridiculous angles, from any type of size, dimension. They're very flexible, and so we chose them for the flexibility because our robot's kind of driving by them. It doesn't. Many times you see the images, it sees it's being this weird angle at the QR code, and it still catches them, which is great. We just didn't think that we'd have the precision to line ourselves up and quickly scan all the barcode. You can get I saw a 42 axis barcode scan. These are the things that they actually use to check out aisles. They have a billion different scans. It's a mirror that spins around, and so you could use that to do it, but it would add to the moving parts on a robot and add to the cost a lot.
You use line following for your navigation.
Yeah.
I was curious if that was a design choice or a customer specification, because you do have a sonar sensor on the robot, so potentially you could learn the layout of the store using the sonar sensor.
True. We could. Our customer told us that we could assume that the store, he gives a lot of flexibility, but that it would not be unreasonable for the store to have some type of lines in it. Actually, a lot of stores even maybe have different colored tiles between sort of around the shelves and around the space for the humans already. So doing something with a line type optimization, a line following robot would be sort of within the scope of this project. To do the sonar sensors, we first need more accurate sonar sensors, as well as then it really comes into a more sort of slam building, model of the store, rather than for us it's point to point following a line. It adds a lot more complexity, but it would be a very interesting and more general solution to the problem.
How well do you work with multiple of your robots in one space? And is there a kind of a density limit that it doesn't work as well afterwards?
So currently, the entire application and demo that we're showing you today is only meant for one robot. But the software and I think almost all the systems that we've developed actually would work pretty well with each other if you were to set up a store in a very specific way, which is to say a single robot is responsible for some set of items. You could say this robot is responsible for these 3 shelves, and this robot is responsible for these 3 shelves, and then you just were to multiplex the orders, which would actually be very minimal work for us. It would be ready, that would be something that we could make ready within a few weeks, if not shorter than that. If you wanted to have multiple robots on the same line, which is something you could do, we'd have to change a lot of our systems to work around that better.
I have a few questions. You said that.
Are we doing on time?
You said that you have problems scaling to on the order of hundreds.
Yeah.
Is there a reason you have a netbook? You have an algorithm that you say runs in n log n time.
It's just because of the fact that the current algorithm, while it runs very quickly for small orders, the huge orders really start to tax it. Our network is not that powerful. It's a pretty low end data. And so yes, if we had an i7 on the server, it would probably overscale to it.
Okay. My other question is, there are other considerations when shopping, I guess, for human shoppers, like you want to pick up some of your groceries last and you want to put your eggs at the top. You don't want to get the milk too, I don't know.
Yeah.
You guys have a way of incorporating that?
So that's something that it's not incorporated in our system today, but it's something that would be not difficult for us to add. It's basically, it changes the, you add a little bit of complexity into the path planning section. You'd have to give some priorities to items. It may even change the algorithm that we use. Maybe not, maybe just have to make more weight to certain paths due to items being fragile, or something like that, and you want to get them last.
And then the last part is, you said that you issue like commands as like drive with this speed and this angle. When the weight of the robot changes, do you have to change what speed and angle you issue to it, or does it adjust for that?
So it claims to adjust for it. It doesn't really. It definitely adjusts a little bit to a point, but only, I'd say, like within like a 10% difference. And if you put a ton of weight on it, it doesn't adjust as much as it would need to. So what we can actually do is we can actually get a notion of our own speed from the sensors themselves. And so we could adjust our speed dynamically based on that.
If you had to do this again, what's one thing you would change?
Oh. Gurwinder said more time, more money. More time's always nice. I think that we get stuff working pretty well, and then we think, oh wow, we could do this even better or something like that. So more time's always better. I guess if you were to think of a specific thing, I would have really enjoyed. I mean, it's mentioned today, we're kind of talking about scale. Maybe trying to, it would take much more time, but trying to do something with multiple robots and manage that, a more realistic grocery full store experience.
All right,
Thanks.
thank you.